Okay. Now, I think we understand what the bin situation is, and we know what the mathematical condition that corresponds to it is. What I'd like to do, I'd like to connect that to the learning problem we have. Okay, so in the case of a bin, the unknown quantity that we want to decipher is a number, mu, just unknown. What is the frequency inside the bin? In the learning situation that we had, the unknown quantity we would like to decipher is a full-fledged function. It has a domain x that could be at 10th order Euclidean space. Y could be anything, could be binary like the perceptron, could be something else. That's a huge amount of information. The bin has only one number. This one, if you want to specify, that's a lot of specification. Okay? So how am I going to be able to relate the learning problem to something that simplistic? Okay, so the way we are going to do it is the following. Think of the bin as your input space in the learning problem. That's the correspondence. So every marble here is a point X. That is a credit card applicant. Okay? So if you look closely at the gray thing, you will read salary, years in residence, and whatnot. Okay? You can see it here because it's too small. Okay? Now, the bin has all the points in the space. Therefore, this is really the space. Okay? That's the correspondence in our mind. Now we would like to give colors to the marbles. Okay? So here are the colors. There are green marbles, and they correspond to something in the learning problem. What do they correspond to? They correspond to your hypothesis getting it right. So what does that mean? There is a target function sitting there, right? You have a hypothesis. The hypothesis is a full function, like the target function is. You can compare the hypothesis to the target function on every point. Okay? And they either agree or disagree. If they agree, please color the corresponding point in the input space, color it green. Okay? Now, I'm not saying that you know which ones are green and which ones are not, because you don't know the target function overall. I'm just telling you the mapping that takes an unknown target function into an unknown mu. So both of them are unknown, admittedly, but that's the correspondence that maps it. And now you go, and there are some red ones, and you guessed it. You color the thing red if your hypothesis got the answer wrong. So now I am collapsing the entire thing into just agreement, disagreement between your hypothesis and the target function. And that's how you get to color the bin. Because of that, you have a mapping for every point, whether it's green or red, according to this rule. Now, this will add a component to the learning problem that we did not have before. Okay? There is a probability associated with the bin. There is a probability of picking a marble and independently and all of that. Okay? When we talked about the learning problem, there was no probability. I will just give you a sample set, and that's what you work with. So let's see what is the addition we need to do in order to adjust the statement of the learning problem to accommodate the new ingredient. And the new ingredient is important because otherwise we cannot learn. It's not like we have the luxury of doing without it. So we go back to the learning diagram from last time. Do you remember this one? Let me remind you. Okay. Here is your target function, and it's unknown. And I promised you last time that it will remain unknown, and the promise will be fulfilled. We are not going to touch this box. We are just going to add another box to accommodate the probability. Okay? And the target function generates the training examples. These are the only things that the learning algorithm sees. It picks a hypothesis from the hypothesis set and produces it as the final hypothesis, which hopefully approximates F. That's the game. So what is the addition we are going to do? In the bin analogy, this is the input space. Now the input space has a probability. So I need to apply this probability to the points from the input space that are being generated. Okay? So I am going to introduce a probability distribution over the input space. So now the points in the input space, let's say the d-dimensional Euclidean space, are not just generic points now. There is a probability of picking one point versus the other. And that is captured by the probability which I'm going to call capital P. Now the interesting thing is that I am making no assumptions about P. P can be anything. I just sort of want a probability, okay? So invoke any probability you want, and I am ready with the machinery. So I am not going to restrict the probability distributions over X. That's number one. So this is not as bad as it looks. Number two, I don't even need to know what P is. Of course, the probability choice will affect the choice of the probability of getting a green marble or a red marble, because now the probability of different marbles changed, so it could change the value mu. But the good news with the Höfding is that I could bound the performance independently of mu. So I can get away with not only any P, but with a P that I don't know, and I will still be able to make the mathematical statement. So this is a very benign addition to the problem, and it will give us very high dividends, which is the feasibility of learning. So what do you do with the probability? You use the probability to generate the points x1 up to xn. So now x1 up to xn are assumed to be generated by that probability independently. That's the only assumption that is made. If you make that assumptions, we are in business, okay? But the good news, as I mentioned before, we did not compromise about the target function. You don't need to make assumptions about the function you don't know and you want to learn, which is good news. And the addition is almost technical. That, okay, there is a probability somewhere generating the points. If I know that, then I can make a statement in probability. Obviously, you can make that statement only to the extent that the assumption is valid. And we can discuss that in later lectures when the assumption is not valid. Okay.